Climate is not static. It varies from seasons to ice ages to million-year trends. This variability changes surface loads and erosion, and the crust responds. Effects of climate variability on tectonic activity. Let's anchor the idea with a timescale bar. Seasonal, interannual, glacial cycles, and million-year orogen evolution. First, glacial to interglacial cycles. We'll draw an uplifting mountain wedge, a glacier cap, and a basin receiving sediment. During glacial maxima, ice scrapes and quarried rock. During interglacials, meltwater boosts erosion. When climate shifted near 1 million years ago, St. Elias in Alaska saw erosion outpace uplift by roughly 50 to 80% by volume. The range lost mass faster than it was built. That can thin the critical wedge, reorganizing faults and focusing uplift zones. In the Alps, cooling and quaternary glaciations increased erosion. Today, about 90% of present uplift measured geodetically is elastic rebound after deglaciation, not active shortening. Takeaway: on 100,000 to million-year scales, climate can govern erosion rates, drive isostatic adjustment, and even reshape deformation patterns. Glacial cycles also move sea level up and down by about 120 meters. We will draw a subduction setting with an ocean, a trench, a forearc wedge, and a descending slab. Lower sea level unloads water mass, can increase coastal incision, and may subtly change normal stress on the megathrust. Higher sea level reloads margins and promotes nearshore sedimentation. These are secondary to plate forces, but they are real external forcings that can imprint cycles in stratigraphy and deformation. On seasonal to yearly scales, surface water mass shifts can modulate small and moderate earthquakes. Consider the Himalaya and the Indian summer monsoon. In summer, rains load the foreland. In winter, unloading occurs as water drains. Observations show roughly twice as many magnitude 3 to 4 events in winter as in summer, about 150 per month in winter versus 75 per month in summer. In parts of Nepal, GPS also shows slightly faster horizontal motion in winter when the hydrologic load is removed. Now, to formerly glaciated shields. We load the crust with an ice sheet, then remove it, and the crust rebounds upward. Uplift rates today can be up to 1 centimeter per year in places like Fennoscandia and Canada. Shortly after deglaciation, large intraplate earthquakes occurred, with fault scarps up to 10 meters. This is transient climate forcing overwhelming tectonic stress for a few millennia after ice retreat. Finally, sediment flux. We draw a sandbox wedge, a thrust belt front, and a foreland basin. Adding sediment to the wedge front increases the load and can stabilize the wedge, shutting off internal thrusting. Removing sediment or enhanced erosion reduces the load and can trigger out-of-sequence thrusting inboard. Field systems like the Himalaya show hints that monsoon strength modulates sedimentation and incision, feeding back on fault activity. To wrap up, climate variability affects tectonics across timescales. Seasonal hydrologic loading can modulate earthquake timing. Glacial cycles reshape erosion and drive rebound that can mimic uplift and reorganize deformation. Sea level and sediment flux act as external forcings on wedges and subduction. Next, we will focus on how climate controls river incision, one of the main engines of relief in active mountain belts.